Let's look at properties of bases. If S equals V1, V2, etc. is a basis for Rn, or a subspace of Rn, then every vector in Rn, or that subspace of Rn, can be expressed in exactly one way as a linear combination of the vectors in S. For example, the set 1, 0, 0, 1 is a basis for R2. Every vector in R2 can be expressed in exactly one way as a linear combination of these two vectors. For example, 1729, Ramanujan's number, that can be written as 17 times this vector plus 29 times this vector. If S equals V1, V2, etc. spans Rn, or a subspace of Rn, but is not linearly independent, then we can create a basis by removing some vector or vectors from S. For example, the set 1, 0, 0, 1, 5, 3 spans R2. You can express any vector in R2 as a linear combination of these. It is not a basis because it is not a linearly independent set. You can express 5, 3 as a linear combination of those two. The set is not linearly independent. We can create a basis for R2 by removing 5, 3 from S. So if you get rid of that guy, now you've got a basis for S. If S equals V1, V2, etc. is a linearly independent set of vectors in Rn, or a subspace of Rn, but does not span Rn, or that subspace of Rn, then we can create a basis by adding some vector or vectors to S. For example, the set S equals 1, 0, 0, 1, 0 is linearly independent, but is not a basis for R3 because it does not span R3. You can't express every vector in R3 as a linear combination of those. For example, just try to express 0, 0, 7 as a linear combination of those. You can't. We can create a basis for R3 by adding 0, 0, 1 to the set. Okay, now when you take these three vectors, now you've got a basis for R3. We have seen that the dimension of Rn, or subspace of Rn, is the number of vectors in a basis. That's how we define it. It is also the maximum size of a set of linearly independent vectors in Rn, or that subspace of Rn. For example, R3 is three-dimensional space. So a set of linearly independent vectors from R3 cannot have more than 3 vectors. Just try to add a vector from R3 to 1, 0, 0, 1, 0, 0, 0, 1, and still have the set be linearly independent. It's impossible. You can't. This is kind of confusing. I'm going to gloss over it, not go into a lot of detail. If V and W are subspaces of Rn, now a caution, that doesn't mean that they're proper subsets. They might actually be equal to Rn itself. A subspace of Rn might be Rn itself. And V is a subspace of W. Again, V might equal W. It doesn't mean that V is a proper subset of W. Then 0 is less than or equal to the dimension of V, is less than or equal to the dimension of W, is less than or equal to N. In other words, subspaces of Rn have dimension less than or equal to N. And the dimension of V equals the dimension of W if and only if V equals W. So a subspace, so if a subspace is not a proper subspace, then yeah, it's going to have the same dimension as the original space. Okay, if the dimension of H equals n, then any set of n vectors that spans H is a basis for H, and any set of n linearly independent vectors in H is a basis for H. For example, since R4 is 4-dimensional, any set of 4 vectors that spans R4 is a basis for R4, and any set of 4 linearly independent vectors from R4 is a basis for R4. We can add this to our monster theorem, our long list of statements which are logically equivalent. We call it the monster theorem. Let A be an m by n matrix. These statements are logically equivalent. A is invertible. The reduced or echelon form of A is the identity matrix. The determinant of A is non-zero. The column vectors of A form a basis for Rn. The row vectors of A form a basis for Rn. This is what we're adding to our monster theorem, that long theorem. For example, add a vector to the set S equals 1, 2, 3, 5, 6, 9, so that S is a basis for R3. Well, I'll use trial and error. So what we can do is we can just add the columns of the identity matrix. Let's add 1, 0, 0 as a third column vector and see what we get. Okay, so when you toss it in, the determinant of the resulting matrix is 0. So this set is not a basis, because by that monster theorem, this set is not linearly independent. So try 0, 1, 0. The determinant of the resulting matrix is 1, 2, 3, 5, 6, 9, 0, 1, 0. Okay, yeah, there should be determinant lines over here. And that equals 6, which does not equal 0. So this set is indeed a basis. delete a vector from the set S equals, okay, 1, 2, 3, 4, 5, 6, 9, 10, 20, 1, 3, negative 1, so that S is a basis for R3. Again, because R3 is three-dimensional, basis for R3 has exactly 3 vectors. You can't have 4 vectors in a basis for three-dimensional space. That would be crazy. Use trial and error. Just delete 1, 3, negative 1. Okay, the determinant of the resulting matrix is, again, there should be determinant bars here. It's going to be negative 27, which is not 0. So the set is a basis.